image of the topological generator, and because u lies in this gamma, it lands in 1 plus these. Okay, so p-adic L functions was first constructed by Kubota and Leopold, and then again by Iwasawa, like by a different method by Iwasawa when f is equal to q, and then in general by Deligne-Ribet using Hilbert modular forms, and by Kassav-Nogus and Barsky independently by using these so-called Shintani's formulas for partial zeta functions or L functions. And so it says that there exists a power series g psi of t such that it interpolates these values. Okay, so g psi of t is a power series. I can evaluate it at u to the n minus 1, and it gives me these L values. And what are these factors? So let's concentrate on the first one first. So L function of so L S rho for any character rho is just rho n by n to the s, and this also has a, okay, so now I am over f, right? So A is a A varies over non-zero ideals of f, and then rho of A I use class field theory to take the map from ideals to Galois group and then apply rho to it. And this, so this is just the and this has a, I should say L 1 minus norm L to the minus s inverse. So there is an Euler product for this, and what I am doing by, oh sorry, there should be a rho. Okay, so I am just removing these Euler products at some of the primes. So I have to remove Euler products at all primes in F which divide P. Otherwise you don't get somehow p-adic continuity if you have those things. So we have to remove those, and this is the complex L function. So there is something I need to explain here. So this thing is a p-adic number because I am taking a power series over Zp. This Zp psi just means I adjoin values of psi to Zp. So I take the ring obtained, the extension of Zp obtained by adjoining values of psi.
Sorry, I forgot. What was U?
Oh, U was on the previous slide. It was image of the topological generator under the cyclotomic. So so u to the n minus 1 is divisible by p. Okay, it has positive p-adic valuation. So this thing converges, and it converges to p-adic number. Whereas on this side I have complex number. This is complex L function, and so this is a complex number. I am just multiplying it by some algebraic numbers. Okay. And then I have to be slightly more careful when psi is 1, because it has denominators. This is related to the fact that zeta functions have pole at 1. I won't get into this. So why does this make sense? I'm writing p-adic number is equal to complex number. This makes sense because of a theorem of Klingen and Ziegel, who proved that independently. They proved that this quantity is an algebraic number, and in fact it can be defined independently of what embedding of q bar you take into C and CP. So it's a slightly delicate point, but the important thing is that these are algebraic numbers. So this is algebraic, that's algebraic, and using this fixed embeddings of q bar into C and CP, I can make sense of this equality. Okay.
So does that power series depend on the embedding of the isomorphism of QP and bar and C?
No, it does not.
It does not.
No, it's because these L values are sum of sort of something psi of something times a partial zeta function, and those partial zeta functions are rational. That's what Ziegel and Klingen proved. So that's why it doesn't depend on that. But it does depend on the choice of topological generator.
Yes.
And and these values uniquely determine this power series. Okay, so these power series over Zp are uniquely determined if you know their values as at infinitely many points. Okay, so how does one construct these power series? So you can, so this thing again began with Kumar. He proved some congruences between Bernoulli numbers, and these congruences were sort of summarized as existence of a p-adic function by Kumita and Leopold, and then as existence of a power series by Iwasawa. So basically you have to prove some congruences between these L values to get these power series. So yeah. Okay. Anyway, the main point is that you get this power series. So now we have two elements in power series. We have one which is the generator of a characteristic of the characteristic ideal of these ideal class groups, and then we have this another invariant which is the p-adic L function. And then one wonders whether there is a relation between them, and indeed there is. So this is the thing. Okay. So again I take. Okay. So this is a bit, because of this twist that I alluded to before, it's a bit complicated to state. But I take f psi mu p infinity, and then I take over this L, and then I take.
But it is not a composed field, is it?
It will be bigger. I mean, because these are both totally real, whereas this is not. So if I take the compositum, it will be totally real, but this is not. Okay, so this is bigger. Okay, and then I have y there. So next I assume that. So at this point, if I don't want to assume this, then I have to classically I have to tensor with QP and work with a PID. But for the moment, I mean, later on in the next talk, I'll show you how to get rid of structure theory from this. So then I won't have to assume this and won't have to tensor by QP either. For the moment, I assume that this degree is not divisible by P. Then I can, then the order of this group is a unit in ZP, and I can again take this y psi inverse omega component. Maybe I have to tensor it with ZP psi. Okay, so everything in here such that gamma of y is psi inverse omega gamma of y. Okay, so something like this. So that's the psi inverse omega component of y, and then by the theorem of Iwasawa that I mentioned, this is a finitely generated torsion lambda module. Actually, this lambda now should be ZP psi, because I have to include values of psi for this to make sense. and there is a typo here. There should be psi's everywhere. Okay, so this was conjectured by Iwasawa and then proved by Mazur and Wiles for f equal to q and Wiles in general, and this follows the strategy of Ribet in some sense. So this is a sort of very deep generalization of Ribet's methods to prove this conjecture, and it says that the characteristic ideal of this psi inverse omega component of y is generated by this power series. So here I have to, in psi equal to 1, I have to include this t to get rid of the poles that are conjecturally there. So again you see this twist of, so I have psi here and then psi inverse omega and then the t goes to, So that instead of t, I have u t plus 1 inverse minus 1. So because u lies in 1 plus p z t, this makes sense that substituting that instead of the variable gives you a power series in t. Okay. So there is this twist that comes in. This is similar to the fact that the information about AI was contained in zeta 1 plus I minus p. Okay, so there is an equivalent formulation due to Greenberg of this main conjecture, which is more useful for generalizations and somewhat neater to state as well. Okay, so now I take the compositum. F infinity this is F cyclotomic F psi. So now I take this compositum F infinity, and instead of looking at L, I look at the maximal abelian P extension, so pro P extension of F infinity, which is unramified outside P. So outside P meaning outside primes above P. So it's unramified everywhere. I mean, I allow ramification at P. Okay, and I call this X. This X is again a finitely generated torsion lambda module. So lambda with this psi now. So there should be psi's in here everywhere. Zp psi t, Zp psi t. Okay, so the characteristic ideal of X psi is generated by these. So this is neater to state. I should have included the next statement in this slide. Anyway, the equivalence comes because X psi is isomorphic to y psi inverse omega, and there is a Tate twist. So this one is the action of the Galois group is twisted by this cyclotomic character phi. Okay. So
is
this
it some reflection principle?
Yeah, this is the reflection principle. Precisely. Okay, so the statement is much neater because of this. So you have psi's in both places, or at least it looks neater. But the other reason why this is useful is that I can take this complex. So this is the étale cohomology complex with compact support. So I take the étale cohomology of spec OF with P inverted, and then I take this T and T is just this as a module over lambda, it's just isomorphic to Zp, but then the Galois group acts on T through this. So Galois group of F bar over F has a surjection onto Galois group of F infinity over F. Okay, and so G of T is just G bar multiplied by T for all G in Galois group of F bar over F, and for all T in T. So that's how this Galois group acts on it.
So T is the group ring. You said it was ZP. It isn't ZP, or is it?
No, T is this Iwasawa. I mean, as a lambda module, it's just lambda.
Oh, okay. Yeah. So not Z. Okay, good.
Yeah, the Iwasawa.
And is there this values of psi again missing, or is that not relevant here?
Yeah, the values of psi are missing. Yeah. Actually, I mean, it's not. it's not strictly relevant here because remember I had this f psi, and then f infinity, f cyclotomic. So this thing just depends on. Yeah, this is not. It's not relevant here because this thing just depends on f infinity. I don't have any psi anymore. So yeah, if I want a psi in here, then I would have to put psi in the values there.
But isn't the Galva group of f infinity
Yeah,
over f, doesn't there a psi involved? It is over f, the Galva group. Oh.
No, but it's over the whole thing.
Yeah.
There is no. I could take different
Okay.
psi's that factor
Okay,
through this.
right.
Yeah.
Okay, good. Yes.
So I can take different components. Of this. Okay. So I can define this complex. This is this compact support cohomology complex. And then how is this related to whatever I have been saying up to now? Is that if I compute its cohomology, then it's non-zero only in degrees 2 and 3, and then in degree 2 it's precisely this x that I had before, and then there is this zp in degree 3. This is again related to the fact that p-adic zeta function should have a pole at s equal to 1 or at n equal to 0 in the normalization that I stated. Okay. Yeah, so I can. So what I'm going to do next time is I'm going to tell you how to reformulate the main conjecture using such complexes, so that gives us that allows us to do two things. Firstly, we can replace this projective lambda module T by other modules, so something like let's say coming from abelian varieties or motives in general. And the second thing is it allows us to replace this very nice Galva group by any kind of p-adic Lie group. Okay, so we need not have ZP cross something finite. We could have any arbitrary p-adic Lie group. And so we no longer need structure theory. So using such a complex, we can formulate main conjecture. We can define characteristic ideals and so on. We can formulate main conjecture without using structure theory. Okay. So what we are going to do next time is we are going to look at determinant of R gamma C. So I'm going to say why all this makes not right spec here. So we are going to look at things like these. Okay, so something like this appeared once in Mignon's talk. So we are going to look at an object like this, and then the main conjecture would say that there exists an element L inside here, which is related to L values. Okay, so this is what Mignon was saying Iwasawa theory does, is that it gives you a canonical element in here, and then there is some kind of p-adic normalization. So this p-adic normalization comes from L values. So next time we will see basically the same talk again with a different formulation of the main conjecture using this language. That's all I want to say.
So I have again a question about this T. This T is not isomorphic to lambda, is it? Because there is this F. It is not F psi.
Yeah, sorry, it's isomorphic to lambda Galva group of F psi over F.
And that still assumes that the order of psi is not divisible by P.
Well, I mean, this is for the next time, and then I won't need any of these assumptions. No.
I have another question. Is there a formulation of the main conjecture that does not involve a choice of a generator, this little gamma?
Yeah, so this is what I mean.
This next time.
Yeah, I mean because our Galva group will be any p-adic Lie group. There won't be.
Oh, great.
Like, yeah. So
okay, suspense. Okay, good. Thanks.
So I'll use K theory. So it's K1. So, but it's yeah.
Thank you.
This is maybe jumping ahead a little bit, but You mentioned Wiles's proof for the main conjecture for the cyclotomic extension over a totally real field.
Yeah.
You mentioned. But that, you don't have to assume the mu invariant zero, right? Because you didn't have to do that.
No, but I just mentioned. I mean, so are you referring to this theorem of Ferrero and Washington about the mu?
No, I mean, I thought that Wiles's proof worked over any totally real field.
Yeah, and he proved
Proved
that.
even if the mu invariant were not zero,
Yeah.
the main conjecture is still true.
Right. So you have mu invariant of these modules X or the psi component of it that we had, and then you have this G psi. So this has a mu invariant, and then Wiles proved that the two mu invariants are equal.
But then in these more general things that you're going to talk about next time,
Yes. Yeah.
people,
I mean, the formulation works without assuming mu is zero, but the proof doesn't work.
so Wiles can prove it even without the mu equal zero.
Well,
So
why?
all
No,
the
but
more general results that I've ever seen have had to assume that mu is zero.
no, but Wiles's result is not equivariant.
Yeah, right.
So if you want to get equivariant versions, you still have to assume mu is zero. Wiles proves it character-wise.
Do you think of that as a purely technical problem, or is it a sort of a foundational problem? Because I remember asking Dr. once, why don't you formulate Bergschwerner diaphragm Tate-Shammer Briggs group as infinite? He said, really, everything goes haywire. It just can't even formulate the correct thing. But here,
About that, I think Gross has a formulation.
oh yeah.
But I think here it's if you believe Iwasawa's conjecture, then of course you should not. I mean, it should
Yeah.
work. But otherwise, I think you have to prove. No, it's not a purely technical thing. If mu invariant is non-zero, then you genuinely have to prove something more.
Right.
You have to prove like deeper congruences in some sense about L values. You can write them down and you can write them precisely what congruences you want to prove, but we don't have any means of showing these congruences.
Except in the more classical case than one.
No, but no, Wiles is again character-wise. If you want to do equivariantly, then it's not. Even in the classical case, we can't do it.
All right. I suggest, yeah, let's meet at